Okay, let me proceed with our main agenda today. Okay, today we try to learn about our last chapter, which is about state feedback control using pole placement. And before we get into that part, as I described earlier, this is the details of test 2 that we try to conduct on Friday this week. So maybe you can respond to this suggestion. I try, what I suggest is that we try to do it on Friday for until maybe this should be 5:30 p.m. 1 hour and 30 minutes. You'll be given about 1 hour 30 minutes time to finish your test 2 solution. And the topic that would be covered would be state space representation as well as signal flow graph. And of course, okay, thank you. Of course, it will be conducted in online mode, and I really I would like to remind you guys that all answers should be in a written form and compile it in a PDF format. And also later on, I will share you the submission link to upload your answer lah. Maybe the link here last time I shared in e-learning. Maybe this time around you can also. I will share you a Google form lah, in order for you to submit your test to answer. And you'll be given about 15 minutes after the examinations period, and I will close the submission link at 5:45 p.m. Okay, that's for detailed info on test 2. And what we try to look today is that according to what I mentioned just now about pole placement control design using pole placement. And we will learn about the concept, and here is most important thing, which is we try to design a state feedback controller, and also try to meet some of the system requirement or transient response specification. And in order for us to get into the design, in part of the design procedure, we will also have a look at the controllability of the system as well. Okay, last time, maybe I put something over here. Okay, before this, yeah. Okay, before this, you know that you have learned several types of controller design as well as compensator. For example, last time you learned about PID, okay, and also you also learn about frequency response, compensator using frequency response, and also compensator using root lockers. Okay, what you learned last time is that you have a system like this. Okay. Let's say I choose, for example, compensator design. Okay, in compensator design, what you try to do is you try to have a compensator which is cascaded with your system. So this is how you meet some of the requirement asked for the system. And also, if you last time as well, when we consider a PID, okay, when we try to design a controller using PID, what's happened over here is that, let's see here, you have a system like this, and you try to get a feedback over here, and maybe I should draw it over like this. Okay, your state. This is a summation block. This is your reference, and you try to come up with a controller also cascaded together. But if we consider a PID controller, this is considered an error-based control system. So why it's called error-based? Let's say this is our reference, and we try to do some subtraction with respect to our system output, and from the results of the summation, or maybe in this case subtraction between the reference input, we come up with a signal which is an error signal, and multiply it with whatever gain of which related to this PID control. Maybe this is a proportional gain, integral gain, and also differential or based on derivative of our error. So that is something that you have learned before this. And this time around, what does it mean by state feedback? Okay, let's say we have a system over here. This is our output, and of course our output over here is our state, right? System state. And let's say we have a reference over here, and here also we have a summation towards the system. And the summation here is, what we try to do is we try to modify the state by giving a multiply with our gain, which is labeled as k, and this gain, normally a negative gain, will be fed into our summation block over here and come up with the control input, or U, for our system. So this is what we're trying to do, and this K, okay, this is known as state feedback control strategy. And maybe you will later on, if you continue your postgraduate study, or maybe if you go through in a bit deeper in your textbook, this gain can be found using maybe LQR, linear quadratic regulator, linear. Normally, this is the one which is very famous. This is also considered as optimal control as well. But the main thing is that this gain can also be found using a placement strategy, where we try to find a gain which is try to modify the pole in our system, modify the pole over here. Okay, modify closed loop transfer function by additional add pole. Okay. And the selection of pole that we try to use, or we try to add into our system, is arbitrary, meaning that we can choose any value of pole in the objective of modifying our closed loop transfer function or our closed loop system. However, the selection of the pole is very, you need to put it, you need to choose it wisely. Otherwise, your system will become unstable, or maybe you will not achieve the specification that you try to achieve for your system. All right, this is the main idea or the general information about what's going on in the pole placement controller design. And this is known as a state feedback, where we feedback the state with multiplication of gain that we try to find, or we try to determine what is the suitable gain for meeting in order to meet our design specification, and later on feedback to our system in terms of input of the system, EU. All right. Okay, maybe later on you can read this through. Here it says that a majority of design technique in modern control theory is based on state feedback configuration. Yeah, because we try to get our optimal design, system design. Of course, we try to have a look at our state, and KID also, um sorry for that. PID also considered as a state feedback, where we try to feedback our state. However, in PID case, we take the error with respect to our reference. So it's a bit different from what we try to see over here. And this is instead of using controller with fixed configuration or forward or feedback path. Maybe for example, a compensator that we learned before this. The control is achieved by feeding back the state variable to real constant gain. So we feed back our state variables, and we multiply it with real constant gain. Okay, I think I've discussed about this in general just now. Poles can be arbitrarily placed. We can choose any poles, and to place the poles or eigenvalues of our system, we need to do it based on our system requirement. So here, says that pole assignment, pole allocation, sometimes it's known as pole assignment and also pole allocation. And what we try to do, we try to placing the poles or eigenvalue of closed system at a specified location. And the location, the specified location is maybe should be based on our system requirement. And later on, this is very important criteria in order for you to proceed with the pole placement procedure or pole placement design control, where the system itself should be controllable, must be controllable. So in order to place your pole in your system, you need to determine whether your system is controllable or not. If it is uncontrollable or not controllable, meaning that pole placement or pole assignment cannot be done for your system. So you need to maybe try another types of compensator, or maybe type of controller. So make sure that you test the system first, test whether it is controllable or not. So that's why I put a video on metrics, I think a determinant of metrics, something like that in our e-learning. But it's okay, because if you have MATLAB, it is very easy for you to determine whether your system is controllable or not. If not, you need to um, do it manually using matrix multiplication, finding the determinant and so on. All right. For pole placement, Okay. Another important requirement is that we need to represent our system in a state space model. So that is very important. So in order to get into or proceed to full placement design, controller design, you need to first convert your system into um, state space representation, whether it is in a form of fixed variable, or maybe you can also use controller canonical form to represent your system. Doesn't matter. Okay, and normally, okay, and also in this course, I will explain to you on how to design a full placement using a fixed variable form state space representation. Uh, Hold on for a while. I need to lower down the volume of another meeting. Okay. Um, this is the theorem background of full placement theory, where here it says that if the pair AB is controllable, then there exists a feedback gain matrix K that arbitrarily assign the system pole to any set of eigenvalues. So you need to uh, here in order to design a pole placement, the first thing you need to determine or to analyze is that is your system controllable or not. If your system controllable, meaning that pole placement is possible. If not controllable, meaning there's no way lah. If you can also do that, but your system is not gonna behave as the desired system response. Okay, and to do that, the first one we need to what do you call it, to analyze the controllability of the system. Okay, to analyze the controllability of the system, the matrix, or if we consider a system state space representation, matrix A and matrix B is very important. These two matrices will tell us whether our system is controllable or not. Okay, maybe later on you will have a look at it. All right, let's say we have this kind of system representation. This is known as signal flow graph. Um, and to tell whether our system is controllable or not, just by looking at the connection of the signal flow graph. If you look at the one at your left, it's considered controllable, and the one at your right is uncontrollable or cannot be controlled. It is because of, if you look at the states and also the input connection, in the one at the left hand side, all states is related or is connected to the inputs, can be controlled by the inputs. However, at your right hand side, not all states can be controlled by the input, where x1 over there, the first state, is independent with respect to the input. Okay, let's say we have a state equation like this. We can say that this is control U affect each of the variable, and we can say that this is a controllable system. However, if you look at this kind of state equation, okay, state variable x1 is not controlled by input U, meaning that this is this is an uncontrollable system. And another way to assess or to determine whether your system is controllable or not is by looking at the matrices. As I mentioned, matrix A and matrix B is very important in your system. So let's say we have this kind of state equation. We have x dot equals to ax plus bu. So the system is completely controllable if we solve this controllability matrix or CM. This CM is basically coming from B, AB, and A squared B dot up until the highest order of our system, which is A n minus 1 times B. And if you solve this and get the rank of this matrix, and if the rank is a full rank, meaning that our system is controllable. Okay, it's very difficult, right? In terms of mathematics lah. I mean, maybe you forgot about how to find a full rank matrix. I'm not going to tell you how to find full rank matrix over here. Maybe you should revise in the background later on. However, I think to find the you have the advantage over here by when we talk about online learning, where you can also use MATLAB in order to determine the controllability of our system. So here, I think to find whether our system is controllable or not is a lot more easier if we have MATLAB to calculate for us. Okay, to calculate it manually, maybe it's a bit difficult, right? Okay, we get into the controller design. Maybe I try to skip this one. Let's say we have this plant represented in state space where we have Ax plus Bu equals to Cx. Consider this is an open loop system. Okay, for designing the pole placement, what we're trying to do that we try to adjust our input over here, which is U over here, modify, not adjust lah. And this input will be substitute with this two terms where we have negative Kx plus R, where if you look at our basic block diagram of state space, okay, if we have not state space, our system for pole placement. Okay, this is our U, this is our states X, let's say, and we have K over here, and we have R, and also negative, positive, okay, K. Okay. Originally based on this state space model, we have U and we have X over here. Okay, this is considered as open loop system. Okay, and this is considered as closed loop system using pole placement. And if you have a look at the difference between these two, we have a summation block over here, which consists of R and also the one that we get from our states as a feedback. So if you look at this point, okay, we can write U as negative k times x and plus our reference plus r. So that's why in this case, we have this equation. Okay, we have these terms where we have negative kx plus r, basically try to represent what's going on in our block diagram of pole placement controller. And if you look over here, the input for our open loop system is just represented by EU. So this basically from here, and this is basically subjected to this equation. And if you substitute U as negative kx plus r and try to rearrange all the, try to group, not simplifies the equation, and you at the end you will end up as this new system or new equation for your x dot, which is this is considered your closed loop system. Okay, and of course for your input it still remain as y equals to cx, and we don't have any plus disturbance over here, because according to this diagram we don't have any disturbance, so we can neglect this part, right? Now our output should be represented by this equation, and our state should be represented by this equation, which is x dot equals to a minus bk x plus br. Okay. In terms of a block diagram, basically I've discussed this in previous slide. So this is the details of that one. So what happened in feedback pole placement state feedback control is that we try to introduce this gain, which is the gain when we fed back feedback into our system based on the multiplication with our current state of the system, right? And if you try to represent it using a signal flow graph, this is the original planned signal flow graph where we don't have any gain or feedback gain, and here is the original plan plus this feedback gain with or k. And if we have three states, meaning that we're gonna have three values of k, and if we have like 4 states, x1, x2, x3, and x2, x4, we will end up with 4 values of k, k1, k2, and k1. So the numbers of gain that we try to put into our system for pole placement highly dependent on the value on the numbers of states of our system plan or original plan. Okay, this is the step for designing a pole placement. Here I have about 5 steps over here. Maybe you can do it in sequence. It is recommended that you do it in sequence, but maybe some of the steps can be settled or can be solved together. Okay, the first one, we need to represent the plan in phase variable form. Okay, basically, if you represent your plan in control canonical form also can, but I think the easiest way is by representing our system plan in phase variable form, PVF. And we feedback each phase variable to input of plan through gain k. And if you remember last time, if we when we try to represent our system plan in phase variable form, we also will end up with getting what is the number of our states, and the number of our states is very crucial in order for us to know what is the, the numbers of gain that we will have in our system. Right, later on, we try to find the characteristic equation from the closed loop system represented in step 2. Okay, from when we know the numbers of gain or k, later on using this, where is it? Oh, sorry. Using this equation, we will try to get the characteristic equation of our system, and there's a method on how to get the characteristic of our system. Later on I will explain to you. And once we done with that, and we decide upon all closed loop post location and determine an equivalent characteristic equation. Okay, we decide the closed loop pole location, okay, based on the system requirement that we desired, that based on the desired system requirement. And of course, we can decide any pole location that we like. However, in order for us to meet the design requirement, you need to decide the pole location based on the design requirement. So that is very important. And maybe at the end, you also need to decide whether your pole location is suitable or not, in order for you to complete your equivalent characteristic equation. Let's say this characteristic equation, the highest order is the third order characteristic equation, meaning that numbers of poles over here should be also 3, and you have to choose all 3 closed loop post location wisely. But that's the technique on how to do that. Later on, I also will explain to you how we can do that. And since we have the characteristic equation based on our system itself and also based on the design requirement, and later on we try to equate, okay, we try to equate and to get what is the value of our gain k. Equate both equations. So we compare the one that we desired with the one that we have, and later on one of the unknown variables over there, which is k, can be determined from that equation. So that is the overall idea on how to design a pole placement. Okay, this is something which is in general, maybe it's difficult to understand, but it's also very important for you to get the idea on how to step-by-step design the pole placement controller. So let's say first we have represented our system in phase variable form, and later on we try to calculate the characteristic equation of the plan. Maybe this is the third step basically. Okay, and number 2, feedback each phase variable into input plan. Okay, this is the one that we consider for our u, where u is equal to negative k, x, in this case also plus r should be included as well. And all right, to get the characteristic equation, what you need to do is you need to find the determinant of this equation. So the equation of the equation that I show over here is very tedious in order for you to solve it, but you need to solve it. You need to find the determinant of this Si minus A minus BK. So the identity matrix over here highly dependent on how many the size of your matrix A and also matrix B over here. Of course, if matrix A is 4 by 4, meaning that our matrix over here should be in the same dimension as well. And we will decide upon closed loop post location based on the and determine the equivalent characteristic equation. And finally, we try to equate the coefficient in order for us to solve the value of k or the value of our gain. All right. Maybe that's a bit difficult to digest because a lot of differential equations going on over there. Maybe some of the calculation is not it's very basic calculation. Sorry, basic equation that I presented just now. Maybe to get a better understanding, maybe we're gonna have a look at example 1. Okay. Example 1, let's say we been given a plan like this. We have g of s, 20s plus 5 in the denominator side. We have s times s plus 1 times s plus 4. And if you look, this is our original plan. Okay, or our open loop system. And later on, if you go to the question, design a phase variable from state feedback gain yield 9%, 9.5% overshoot and settling time of 0.74 seconds. So these two is our system requirement or our desired system performance. And our strategy to place our pole location must be based on these two design requirements. Otherwise, we can say that our system is not cannot meet the system requirement or the desired system performance. Okay. Solution. First, you need to represent your plan in phase variable form. And based on what we have over here, this is the system, the plan in phase variable form. And to convert from this transfer function to be represented like this, I've explained to you on the steps to be taken in order to represent your plan in whatever state space form. I mean, in either phase variable or controller canonical form. And feedback each phase variable to the input plan through gain k. So we define our gain or define our input over here as u equals to negative kx. Okay. And from this u equals to negative kx, we find the characteristic equation for closed loop in step 2. And since you define your what do you call it, u equals to kx, so it will transform your system equation to become a minus bk. Maybe I try to write down over here, maybe over here. Your system basically x dot A minus BK times X plus R. Okay, and I think this is should be B times R. Oops. Okay. Why I cannot erase this one? Let's see. Okay, we will try to use this equation back, B plus R. But basically, if you don't have that one, also can. The most important thing over here is your system plan over here. And using this portion, this term, what you're trying to do, you try to set up your matrix according this in this form. For example, originally you have this matrix. Where's this matrix? Okay, originally you have this matrix X dot equals to E X plus BU or BR in this case. Okay, since you um, replace U as U equals to negative K X, okay, plus R, okay, this equation had become like this, negative A minus BK times X. So you need to modify, or you need to write down in the phase variable form again, where in this case your phase variable form will become like this. X dot equals to, okay, the one that we have up here is remain. Okay, the one that you have in the second row also remain. Okay. Okay. The changes only happen at this portion, where here we have negative K1 minus 4 plus K2. Okay. And here we have negative 5 plus K3. Okay, remember that how do we get this one? Okay, this one is coming from A minus BK. Okay, we focus on this part. First, A, we have a matrix which is looks like this: 0, 1, 0, 0, 0, 1. We have what is the matrix before this? Is it here? No. 0, negative 4, negative 5. 0, negative 4, negative 5. This should be 0. Okay. Minus, okay, minus, what is your matrix B? Tells you your matrix B over here is 0, 0, 1. 0, 0, 1. 0, 0, 1. And what is the dimension of matrix K? Okay, in this case, to, let's say this is 3 by 3 matrix, and this is 3 by 1 matrix. Okay, what is the dimension over here, you expect? Is it 3 by 1 or 1 by 3? 1 by 3, yes, of course. So in other words, our matrix K should be looks like this. K1, K2, and also K3. That's why if we have a 1 by 3 matrix over here, okay, this is 1 by 3. So at the end, we will have 3 by 3 matrix minus with a 3 by 3 matrix over here, and the results from that will lead you to this matrix, or at the same time this matrix actually. Okay, this is the results of solving these matrices, which here we have A minus BK, and it is very um, important that you know this matrix K should be in the form of 1 by 3 matrix. Okay, once you have this A minus BK matrix, in order to get your characteristic equation, okay, you need to find the determinant of Si minus A blah blah blah. Okay, how do you do that? Maybe I need another slide over here. Let's take this equation back. Say this is the equation that we try to find. Okay, the characteristic equation should be looks like this. Okay, remember that when you try to find a determinant, okay, first of all, find what is the dimension of this Si. Okay. Si should be a matrix which is set up like this, or a diagonal matrix in the size of 3 by 3. Dimension of the matrix is 3 by 3, and you minus, okay, maybe that is Si, so this one minus, okay, 0, 1, 0, 0, 0, 1, negative K1, here we have negative 5, is it negative 5 just now? Negative 4, negative 4 plus K2, and here we have negative 5 plus K3. Okay, this is the matrix that you should consider. Maybe I should write this over here. Why I don't have the eraser? If I have the eraser, it's a bit easier. I can erase this one. Okay, this is basically our how do we solve this equation, and we need to find the determinant of this matrix. First, you solve the subtraction, and later on you find the determinant of this matrix. And determinant of this matrix is basically you try to find the determinant of 3 by 3 matrix using whatever types of method that you know. So that's why I put a video for you in e-learning for you to get the revision or revise back on how to handle determinant of 3 by 3 matrix. And of course, in your case, I think the highest order that I try to give you guys in your assessment, the highest will be up to 3 by 3 matrix. In other words, the highest order should be a third order of differential equation. Okay, that's when we find the determinant of this matrix, you will end up with this equation where we know that the highest order over here is s to the power of 3, and later on continue s to the power of 2, 1, and 0. So this is the characteristic equation of our closed loop system when we add our arbitrary k in our system. Okay, now what we try to do next is we try to decide we try to determine the desired characteristic equation. So in this case, our desired characteristic equation can be found by solving, based on the design requirement that we have. So it is very important that you need to have a look at the design requirement. Here we have our shoot and also our settling time is part of our design requirement. And from here, you find the zeta and find the omega m. And if you know zeta value and omega m value, you can find those two poles that should be in our system. Okay. Now, if you look at the poles that we have now, we only have 2 poles. But our system, originally we should have up until 3rd order, meaning that this 2 is not enough. We need 1 more pole in our system. But to get the most dominant pole for our system, first we need to have a look at our desired system performance, and from there you can calculate your desired closed loop characteristic equation. But that is only based on 2 poles that from our system requirement that we have over here. And from these 2 poles, if we, let's say we have s plus 1, for example, let's say we have another one, P2 is s plus 2. Okay, if we expand, this will lead us to the highest order will be s to the power of 2 and 3s plus 1. So the highest order over here is s to the power of 2, still not matched with what we have in closed loop characteristic equation. So you need to choose another pole which will make our system to become the highest order should be in the power of 3, order of 3, 3rd order differential equation. And how do we do that? Meaning that we need to include 1 more pole, s plus y. Okay. These 2 based on the desired specification, system specification, and this, the other one is based on our try and error, or sometimes not try and error, but we need to strategize the selection of our 3rd pole. Okay. Now, based on the system requirement that we have over here, overshoot and also settling time, we have calculated 2 poles, P1 and P2, and it gives us this value. So this is considered as our first pole, and this is another pole. It is a conjugate pole where we have the first at J plus J7.2 and another one as minus J7.2. So it is considered our poles number 1, poles number 2, the most dominant poles that we have. And we need to select the 3rd poles, which in this case we can choose any value of pole. Okay, any value of pole. And suppose that the selection of this third pole should be based on our, okay, back to our system. If we choose to add poles that can cancel our zeros or our numerator part, then that should be our system should be more stable. Okay, so the idea of choosing the third pole is that this third pole able to cancel our zeros at the open loop transfer function. So that's why here I choose negative 5.1 as my third pole. And of course, I also can choose negative 5, and it is completely cancel our system. But for this is for demo purpose. For demo purpose, I choose negative 5.1, and the value over here, maybe you can also choose like 10.1 also can, maybe you can choose 1.1 also can, negative 1.1. It is arbitrary being chosen. All right. Later on, once you have your third pole, okay, now you have 3 poles in your hand, and you need to find the desired characteristic based on these 3 poles. And how do you do that? You multiply all those 3 poles. For example, in this case, we have, maybe I should erase this one first, and this is P3. And how do we get to this point? Basically, what you do is you have S plus 5.4 minus G 7.2. My first pole. Second pole is S plus 5.4 plus 7, G 7.2, and my third pole is S plus 5.1. To find the characteristic equation, you solve this equation. I mean, you solve these 3 terms, expand. And of course, if you look at here, we have S1S, second S, the third S. So the highest order should be S to the power of 3. So this equation basically coming from this calculation. All right. From there, okay, now you have, oh, I cannot do that. It's okay. Okay, from here, we have 2 equations, which is one given by this equation, okay, okay. Oh, all right, I have it here. No need to copy and paste. Right. The first equation that you have in your calculation, we have your characteristic equation, which is coming from your closed loop system, where this is coming from the determinant S I minus A minus B K. Yeah, this is coming from this equation. Okay, this part. And this part is coming from P1 multiply with P2 and multiply with P3. Okay, you see both equations are characteristic equation, but the first one coming from our closed loop system, and the second one coming from the desired specification. So what you try to do is you try to equate this parameters or this term in order for you to get what is the value of your K1, K2, and K3. For example, I take this portion, okay, I have 0 plus K1 equals to 413.1. So my K1 is actually equal to 413.1. For K2, say over here, I take 4 plus K2 equals to 136.08. Rearrange this equation, put it on the left hand side, you will end up with your answer of K2. So that's what it means by equate both equations. So the first one, you need to calculate the, or you need to find what is your characteristic equation based on your closed loop system, and later on find the characteristic equation based on desired system specification. And at the end, this is your state space representation of your closed loop system. See here, we have, this is negative K1, this is negative K2, sorry, let me see. This is 4, no, it should be over here. Okay, negative 4 plus K2. Okay, this is negative 4 plus K2. Negative 4 plus K2. This is negative K1. And this is your negative, this is a bracket over here. Negative 5 plus K3. Okay, and you just write it in its numerical value and find what is your state, what is the value of that particular elements. And of course, we have a phase variable form. So the phase variable form, normally we have diagonal value of 1 over here and 1 at the bottom for our input. And finally, for our C matrix, according to what we have in our system, we have, this is basically coming from the numerator side. Okay, the numerator side of our system, basically the same as what we've seen earlier in the question when we represent our system in a phase variable form. And from this state space representation, you can also convert it into a transfer function. And I think we discussed about converting this state space model into transfer function in our previous class. So you need to know how to set up this transfer function as well. And at the end, we will have this kind of transfer function of our system. Basically, it's very simple. The transfer function, if you look at the denominator side, basically you have calculated this part. This part is the characteristic equation based on our system, based on our poles that we expand. And this is this part is basically coming from the original question, which is we did nothing, we haven't modified anything from this part. So that's the idea of finding the value of K. And if you try to simulate this example in the system, you might find that when you put a step response to your system, here overshoot is 10.11%, settling time 0.66. You see that here it's met our requirement, but in terms of overshoot, we the design requirement have not been met, so we unable to meet our design requirement. So what we try to do here, we try to just modify our third pole value. So our third pole value, if we put it as -5, and we try to recalculate our characteristic equation, of course, when we do the simulation, you will get your system specification or the desired system performance that you like in for your system. So that's all for designing pole placement using pole placement method. You have any question? Have any question? Guys, are you there? Easy? No, doctor. Is it easy or so lah? Okay. I think we're gonna take a break about 3 minutes time. 3 minutes or let's say 3 minutes. I would like to go to the toilet. And we will continue back after that 3 minutes and discuss about how do we implement it using MATLAB software. Okay, I'll see you again at 12:17. Okay, welcome back. You guys there? Still there? what I understand before class is quite confusing since it's have different between root locus and pole placement. Here. What do you mean, Lim? For pole placement, basically what we're trying to do is the structure of our control system is a bit different when compared to what we have in a root locus design. Root locus, normally we try to put a compensator, right? And it's like cascading towards each other. And in this case, we try to have a feedback control. And the feedback in our feedback, we try to assign a gain which is based on the selection of pole by modifying the pole. We try to select a gain which can modify our system poles. So that's the difference between the root locus and the pole placement. I think the idea of modifying our system by assigning a pole with scaling also, something like that lah. Feedback control with scale, because the scaling that you mentioned over here is by by putting a gain at your by scaling your input state by putting a gain in your feedback, and also at the output side you will at output and input side you can also scale your input or your output based on this feedback controller that we try to design. All right, we'll have a look at MATLAB. Okay, here. Okay, this is the exact example from what we have in our lecture notes. Okay, but before that, I would like to show you one example, which is a basic example. We go to the basic one. Later on, we try to have a look at what we have in example one in our lecture note. Okay, let's see. We have a, can you see? Let's say we have a system plan, which is like this. Cannot make it bigger. Right. You see it? Or should I make it bigger?
Yeah, we can see it, Doctor.
Okay. Let's say we have this system, yeah. Here. Our system plan is, this is numerator, and this is our denominator. And we can easily convert our system, these two matrices into a transfer function by using this instruction, where we have ng 4, dg2 is 1540, and we try to convert our system into a transfer function using, I don't know how to make it bigger. Maybe there's a view over here. If I don't have view, not here, but never mind. Okay, this is our system transfer function, which is coming from the definition of our plan. Try control Okay, I tried control and plus. Where's my plus? Cannot lah. Try symbol plus. Cannot lah. Okay, never mind. Maybe if you have this script, I think this script, is it available in your e-learning? Maybe I should put it in e-learning later on. Okay, let's say this is our plan, and this is our system, which is our system transfer function. And from this system transfer function, okay, we can convert into a state space by using this instruction, this code, where we have A, B, C, D. Where is our A, B, C, D? Okay, equals to transfer function to state space. Okay, this is transfer function to state space, our numerator and our denominator, and it will define our A, B, C, and D matrix over here. So now we have A matrix, which is a line, or which is written like this. We have -5, -4, 0, 1, 0, 0, 0, 1, 0. We have B as 1, 0, 0, and C as 0, 0, 4. And basically, this is a control canonical form. Yeah, this is control canonical form, and you can use all this information to control, to design your controller. And let's say we have a system parameters which is like this, and for designing a pole placement, basically we can use this instruction k equals to place A, B1, B2, A2, B2, and our poles. And before that, we need to define what is our poles. In this case, I define my poles as -2 plus J2, -2 minus J2, and -5. So this is the three poles that I define. Maybe you can have a look at the description that I have over here. Poles value can be randomly selected or based on desired system requirement. In this example, poles value are randomly selected. I select these three poles and put it in 1/3 matrix. So this is the matrix of our poles, or our the matrix that we will use in order to design our controller. And later on, to get our value of k, or our gain value, we can use this instruction where k equals to place A2, B2, and the definition of our poles that we decide just now. And make sure the dimension of our P, or our poles that we selected, should be aligned with the dimension of our system. Let's say here our system, in our system we have matrix A, which is a 3/3 matrix, and you see that for matrix B we have 3/1 matrix. So meaning that for matrix P, we should have a 1/3 matrix as well. So now, as I evaluate this, okay, this is the value of k that we MATLAB has automatically calculated for you. So maybe it's not that clear if you just look at the command window. So let's see what how it looks like when we put it in a Simulink diagram. Okay. home preference font. Yeah. See, home, where is it? Preference, font. Oh, okay. Actually, what I like to do is I just like to resize the view. But if this is part of the idea lah, to option that I have, but it's okay. Maybe later on, if you have the this coding, maybe you can try play it around. Okay, let's say we have this block diagram. Okay, now what I try to do is I try to show you guys the response of our open loop system first. So if you look at our workspace just now, we have defined two open loop system. The first one is in transfer function form. The second one in a state space form. Okay, for transfer function form, what you need to do is you just need to put in the numerator coefficient and also denominator coefficient, which is in this case is NG2 and DG2. And for state space, for state space, you need to define your parameter of A, B, C, and also D. So that's why if you look at my workspace just now, okay, first one I have my NG, NG2 and also DG2. These two will be used in my transfer function block. And I have A1, A2, B2, C2, and D2. These four components will be used in my state space block. So now I have my state space block defined as A2, B2, C2, and also D2. So what I expect if I put a step input in my system, I should expect that this value should be a same value for both signal. So the signal will be overlap each other. This is considered as my open loop system. So if I simulate my open loop system, okay, this is what I expect. So this is the result. So if you see here, both signal has overlap each other. This is open loop system. Okay, and remember that we do have a system requirement like overshoot, like settling time, something like that. So based on this open loop system, of course, the system is unstable because it keeps on, the response keep on increase as with respect to time. So this is undesirable response that we see in an open loop control system. So just now we design our pole placement, right? So our pole placement, we have in our pole placement we have our gain, our gain. We decide what is our pole, and later on using the instruction of place A to B to and P, we will MATLAB will automatically calculate our gain. So the gain should be placed over here. Should be placed over here. And maybe you would like to ask, what is the difference between this block and this block? Basically, it is the same. Okay, this block is open loop, and if you look at the block that I have down here, is a closed loop block. So basically, if you would like to have an open loop simulation, you should this diagram should be represented like this. So this is basically, this is the same that what we seen over here. Let's say we simulate, and of course the result will be the same. Okay, this is what we have earlier, and this is what we have in the second block diagram. And to make it easier for us to look at it, maybe put it like this, and okay, connect over here, and we simulate it again. Oops. Okay, it's identical. However, okay, the one that I have in is now, okay, like this, right? So the one that we have over here, the gain here, is calculated based on the definition, based on our poles that we decide, and by using this um, instruction, or k equals to place A, B2, and P. So based on this instruction, what we found out that our k is 4, 24, and 40. This is basically k1, k2, and k3. And it should be, if you mix it, if you confuse which one is k1, k2, and k3, maybe you can try by putting it in your block diagram over here. This should be your k1, which reflects your x1. This should be your k2, which reflects x2. This should be k3 that reflects x3. So if you run the simulation, what we have over here, maybe I should make it comparison between closed loop and open loop. Let's say these two, the one that at the top over here is basically an open loop system, and here we have a closed loop system, and I put it the signal together for us to make the comparison quite easy. Okay, if you look here, it's quite difficult to analyze our system because the open loop system is keep on increasing and the range getting bigger and bigger. So it's quite difficult lah. Basically, this is what we have in the control closed loop system. And if you look at the closed loop system over here, we have, this is what we have. And you can determine, or you can analyze what is the overshoot of the system, and also what is the settling time. Is it met the requirement of our design or not? So that is one of the what do you call it? One of strategy that we can use in order to design our pole placement system in MATLAB. And the other one is like this. I think if you use this kind of block diagram is much easier, where here you have a step input. Okay. Your step input, your original state space, this is your original definition of your state space, A2, B2, C2, and also D2. Basically the same, but I write C can also be written in terms of diagonal metric as well. Okay, and at the end, to put your gain, what you need to do is you just get the block diagram of gain and put it as a multiplication of matrix K times U. So here we have, if you look at a block diagram output, state space block output, basically this is a vector, and vector over here we have 3 by 1 vector. We have x1, x2, and also x3, 3 by 1. So of course, this should be a matrix coming into here. And K we defined earlier that K is a 1 by 3 matrix. Here, K as 4, 24, and 40. It is a 3 by 1 matrix. So that's why you need to multiply your multiplication over here should be in the form of matrix K times U. And all the matrix can be easily multiplied. Otherwise, you need to do it one by one like this lah. Okay, and of course, the response over here, our output should be the same that we seen up here. Same. Okay, right. That is one example. This is basic example of pole placement. We don't have the question in our lecture notes, but this is what how the pole placement looks like in MATLAB MATLAB software design. Okay, and the other one I would like to show you is the one that we have in our lecture slide. So this is the one. Okay. I don't know whether this command window can be, we can make it bigger. Can we make it bigger? Cannot. Cannot. I don't know how to do it. But anyway, if you look at the example that we have in our lecture note, okay, here is the example. Okay, this is our system. And where in our system, we have this transfer function, which can be defined as instruction over here. Right? We have numerator side, we have 20 times s plus 5, so it can be written like this, 20 times 1, 5, bracket. For denominator side, since we have multiplication of s plus 1 plus s plus 4, so you need to make a convolution between those three elements. So here we convolve, or we did the convolution of s and convolve with s plus 1 and also s plus 4. So this is how we write in MATLAB. And we have the uncompensated system as transfer function, numerator, and denominator. So let's see if we here. Let's see what happens if we have this uncompensated system. Is it the same? All right. It is the same as what we seen in our lecture slide. We have 20s plus 100 at the top or at the numerator side. We have the multiplication or the differential equation of s to the power of 3 plus 5s power of 2 plus 4s at the denominator side. So this is the one that we have for transfer function. And to represent the system plan in phase variable form, basically for phase variable form, I did it manually, but you can also do like this. Yeah, you might also do it like this, where you will have, let's see, okay, let's say we have this transfer function num n say we simulate this one. Okay, it will give us the controller canonical form of our system, and you rearrange it back and put it in a phase variable form, because I think phase variable form is a bit easier compared to in order for us to understand and also to make the calculation manually. And okay, the first at the top over here is controller canonical form, which is you can is another option that you can consider. But in this case, if I in your position, I think the first one I will proceed with this controller canonical form, and later on from this matrices, I'll convert it into a phase variable form. It's very easy to convert it. You need to make sure that all these elements have been shifted and also been shuffled between each other in a different position. All right. Let's say we consider our phase variable form in the form our system in the form of phase variable, and remember that earlier in the class I said that in order for us to perform the pole placement controller design, first we need to check the controllability of our system. So to check the controllability of our system using MATLAB is very easy, because what you need to do, you need to use these two instruction. Basically, one also enough, but normally we will use both instruction in order to determine whether our system is controllable or not. The first one is CO. CO also can be, maybe you might put it as CM also can. Okay, CM is controllable. CRTB, AB, or let's say here I put it as CO. Okay, now what do we get from these two instructions? The first one, we try to find what is CO. CO is, we try to find our controllable matrix. Controllable matrix is basically the matrix that I show you over here. All these calculations, okay, CM, B, A, B, A squared, B dot 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 up until the highest order of our system can easily be calculated using this instruction. CO equals to CTRB AB. So this is very easy for this to make the calculation becomes easy. To make it manually, of course, you need to spend time to do that. But with MATLAB, just type this instruction, it will give you what is the controllability matrix for your system. And the controllability matrix of our system, remember that our A is 3 by 3. Normally, the controllability matrix also in a 3 by 3 matrix as well. So here you can see that my controllability matrix is represented by this matrix, this 3 by 3 matrix. And I also, this is a suggestion from MATLAB as well. In order for you to find whether your system is controllable or not, use this instruction, which is you have unco equals to length of A minus rank of CO or co. So if the answer of this unco is 0, meaning that your system is controllable. Unco means uncontrollable, uncontrolled state. So in this case, unco is equals to 10, meaning that your system will be controllable in this case. And another way to determine whether your system is controllable or not, according to what I mentioned in my slide, you need first to find what is the rank. Okay, the rank should be full rank. Okay, Or you can also evaluating its determinant. Okay, if its determinant turns out to be 0, then it is rank deficient. Otherwise, it is full rank. Okay, then that's why here I put determinant co. Okay, determinant of my controllability matrix. If my determinant over here, the result of determinant co is 0, means that my determinant is not a full rank matrix. So here my determinant is -1, meaning that my system is controllable. So although you see that my slide is like very simple, but a lot of important things that I mentioned in the slide as well. So you need to really have a look at go through the slide one by one, and also get the understanding. So remember that you can check your if it is a square matrix, of course, you can check whether it's full rank or not by using its determinant as well. Okay. Right now, we have checked our metric, which is controllable, so we can proceed with our design of our pole placement state feedback controller. So now you see here in the example, I have a performance index where I would like to achieve. For example, I have overshoot, which is 9.5%, which is 0.095 if you would like to write in MATLAB, and you have settling time, which is 0.74. Okay, no changes to that. And also, if you remember that in order for us to calculate what is our, where is it? Okay. Where is it? Okay, is it here? No. Okay, here. In order for us to get the desired closed loop characteristic, we need to find what is our zeta and our omega n. And from there, we can find our dominant closed loop poles. And our dominant closed loop poles should be the combination of our zeta information and our omega n information. So here is the equation to find those two poles. And of course, if you try to do it manually, also can, but if you have MATLAB, why not use MATLAB? So here I put the calculation of zeta, which is given that we have OS over here, just put the value of OS, and also the value of our TS over here to find what is our omega n. And the equation that I show in the slide can also be written as this one, where in this case, if you have this, let's see what happened if we evaluate the selection. Okay, using this definition and also the equation that I plotted over here, I write it over here, I can get what is the value of P1 and also P2. P1 and P2 is given by -5.4 blah 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 plus J 7.2, and also -5.4 minus J 7.2, and we done with our dominant closed loop poles. And to get the desired characteristic equation, we have two poles over here and one pole to choose. Here, the desired for desired characteristic equation, I choose the third pole to be selected as -5, okay, or P equals to -5, and in this case, it will lead me to a pole of S plus 5. And to multiply all these three poles, P1, P2, and also P3, what I need to do, I need to do some convolution. Convolution First, I convolve these two poles, and the result of convolution of these two poles, I convolve it again with my third pole over here. And at the end, I will end up with my characteristic equation as 115 and so on. Maybe I try to evaluate first. So this is my characteristic equation in matrix form. Okay, in MATLAB language lah. But you can also write down or here you need to interpret which one is which. For example, in this case, I have 1, this is 15.8, this is 135, this is 405. This is basically for s to the power of 3, this is s to the power of 2, s to the power of 1, and s to the power of 0. So you need to really understand the language of the MATLAB, how MATLAB handle your data or your calculation. Okay, and to make my life easier, I also would like to find my closed loop characteristic equation, but in this case, it involves parameters or variables of K1, K2, and also K3, and I cannot do that as easy as I like. I need to define my calculation in terms of systems, SYMS, SIMS. And at the end, okay, based on this instruction, I will get my characteristic equation as K1 plus 4S plus K2S plus K3S squared plus 5S squared plus S cubed. So this is basically my characteristic equation where I need to further improve it. Where if you look here, the s to the power of 3, later on I will compare it with what I have over here. And s to the power of 2, I need to combine these two because both are s to the power of 2. I need to compare it with this value. And for s to the power of 1, I just need this one. I need to compare these two and to combine these two and compare it with this element for s to the power of 1, and for s to the power of 0, which is represented by this value because this is directly the value of K1. And later on, you might ask, where is our answer? Basically, our answer is the comparison, the value of K that we compare between our characteristic equation and also our desired characteristic equation. So I think this this example is available in your e-learning. Okay, you can later on have a look at it. Okay, let's say we try to simulate our system. Okay. Okay, let's say we simulate our uncompensated system first. Another way, if you would like to simulate your system without using Simulink, you can also use this instruction. I hope that you have a look at this instruction later on. Okay, now we first maybe we should clear all our definition first. Right, here we have our uncompensated system or open loop system. And for the compensated system, we have numerator as the same as what we have in the uncompensated system. And for denominator, we have this coming from the characteristic equation that we found earlier. And this is the transfer function of our closed loop compensated system. And we try to simulate our uncompensated system first, and then what's the result? I'm still busy. Sorry, yeah, I'll take some time to show you this one, because later on Thursday I will show you um, the exam. Not lah, I will show you what I would expect in your final exam, because this question is confirm one question 25 marks in your final exam. So that's why I really focus on explaining as much as possible that I could. Okay, if you look at here, our step info, of course, based on our system over here, the rise time is NAND, settling time is NAND, overshoot also NAND. This is an unstable system. So what happens if we have a closed loop system? Maybe I should not put it as hold on. I just evaluate this part. Evaluate lah. Where's my, okay, this one. All right. And the step info. Okay, now if you see here, this is the system, the closed loop system response. And with when we put on the gain of feedback gain in our system, and what we see over here, the settling time is 0.66, which is met our requirement, because our requirement is 0.74, if I'm not mistaken, just now. And our overshoot should be 9.5. And here we have 9.4773, which is achieve have met our system requirement. So that is how we design our pole placement controller or state feedback. Maybe this is another way in order for you to get the answer. But I think up until this part, it's enough. And if you try to maybe ask about what is the actual answer for this question, okay, maybe I would say that the answer for this question is the value of K that you have in your system. I give you a sneak peek of what we have in final exam. Maybe later on we will discuss this one in Thursday class. Let's say this is the question. We have, okay, maybe this is coming from previous years. And we have UFSS, submarine over here, submersible. And this is the transfer function that we would like to design, or this is the system that we would like to improve, where the settling time is set as 0.8 and the overshoot is at 5%. And at the end, you need to justify the selection of your third pole. Maybe the selection of third pole most likely depends on the value of your zeros over here, or the numerator side of your system. And the answer here, I will share you my answer. Okay, this is what I have in the solution. The first one is the transfer function. Later on, we convert it into a phase variable, check the controllability matrix. Here, this is not an easy task. You need to really do the calculation manually. This is from 2018, 2019 semester 2, which is, I think the students need to calculate it manually, still need to calculate it manually. And later on, you should define your control input as this one, and you find out what is the characteristic equation from that one, and you need to calculate the second order poles that satisfy the desired requirement. Once you did that, you need to select the third pole, and the selection of the third pole is the justification here is by using zero cancellation, where you try to cancel the zero at the numerator side of your original transfer function. And finally, you find the desired closed loop characteristic equation and find the gain. So this is the ultimate answer. I mean, the answer of the question. You need to find what is the proper value of gain for to meet the design requirement of your system. So basically, out of 24, the last part only gives you about 4%, 4 marks, and the rest coming from the strategy that you provide over here. This is the simplification. The answer scheme over here is the simplification, simplifies one. Basically, to get from this transfer function into a phase variable form, you need a proper step to do that. I gave you your the exercise for you to practice. Means suppose that you know how to convert the transfer function into the phase variable forms, because it is very important in this case. Okay, I think I've took about 5 minutes extra this time around, but maybe later on we will discuss about this solution and this question as well. And one more question that I asked students during the pandemic time, where in the solution you need to simulate the system as well. Okay, I think you have any question? Okay, Lim.
Doctor, so during final exam, we need to use MATLAB to simulate the questions, or we just do the question on paper only?
Okay, that's the thing that I would like to highlight in next class basically. But since you asked here, yes, of course, you need to use MATLAB. In terms of answer, you need to provide the manual calculation and also provide the simulation result with the coding that you use to produce the result.
Which means final will be include chapter 9, is it, Doctor?
Yes, chapter
Okay,
9 will be one of the question in your final exam. 25 marks over there.
okay, that, Doctor.
Okay, any question? I think we shall meet again on Thursday. That is it okay? Because I already took about 6 minutes of your time over here.
It's okay, Doctor.
Okay,
Uh,
doctor.
Doctor, last question. In e-learning, Doctor already upload the solution, example one for placement finding, if I'm not mistaken, but that file cannot be opened
Okay, which file? Yeah, wait. You mean
above the IEEE conference paper
this
template,
one?
Doctor. Yes, Doctor.
Oh, okay. I will. Um, eh, can lah.
Can open because I tried 2 times already cannot open. Maybe I try again later.
Okay. Oh, this is like the one that I described just now in my slide, where the first one you need to get into the phase variable form and you define your input plan, this is calculation for characteristic equation, and how do you multiply all those things, and this is how you find the determinant of in order to get your characteristic equation. I think it can be open. Maybe I'll share it again later on. Is it okay?
Sure, Doctor.
Ah, uh, Brian, you can or you can't? Can. Brian can.
Oh, yeah, I need to reload again.
Oh, okay. All right. The rest, I think this is the coding to find the desired closed loop poles. Uh, Coding for to find zeta, omega n, and also the poles. The other one is the coding as well, if I'm not mistaken. Coding to characteristic equation. Yeah, this is characteristic equation. I think it's more than enough in terms of the coding that you need to have in to solve this problem. Do you still need this coding as well? The one, oh yeah, I closed the MATLAB already, but it's okay. Maybe we can discuss it later on Thursday. Okay. All right. I hope that what I explained here can enlighten you guys uh, in terms of um in terms of try to understand what is the pole placement in general, and also what do you expect the I mean what do you expect in your assessment in terms of chapter 9 with respect to chapter 9. With that, I think we'll see again next Thursday. I hope Joda also will not overslap again, because very crucial, Joda, this time around. This is 25 marks in your final exam. Hopefully you try to get a full understanding on how to do it, because this is not like uh, I've mentioned already. This will definitely inside your final exam. All right. Okay. With that, thank you so much for your attention, and I really apologize for taking up to 10 minutes of your time, extra time. We'll see you again on Thursday at 9 a.m. Okay. With
Sure,
that,
Doctor.
thank you so much and take care, everyone. Be safe.
You too, Doctor. Thank you, Doctor.
Okay.
Thank you.
Thanks, Doctor.